So this video is about reaction types and how to guess the possible reaction types, their products, and how to balance them. But before watching this video, I suggest making sure you understand how to name ionic and covalent compounds and how to put the formulas together, because that's the basis of it over here for writing these reactions. I'm going to explain a little bit about how to do that over here, but if you want to learn about them in details, I'll tag my other two videos over here that it shows you how to name ionic and covalent compounds. So the first type of reaction is called synthesis. So in a synthesis reaction, what happens is two elements or compounds, they combine together and they end up becoming one compound. So let's say A plus B always gives us AB. So what happens here is that based on what they are, sometimes they're both non-metals, so they combine together to make a covalent compound. Sometimes one of them is a metal, the other one is a non-metal, so they make an ionic compound. So based on what they are, they can combine and make either an ionic compound or a covalent compound together. So let's do some examples for that. Let's say we have sodium solid plus chlorine gas, and together they want to combine and make us a compound. So here we look and we see sodium is a metal. However, Cl is a nonmetal, so together they make an ionic compound. So whenever you write an ionic compound, you have to put them based on their charges. So the charges matter. So Na has a charge of +1, Cl has a charge of -1. What happens is that you can switch the charges, kind of put it as a subscript underneath each other. So Na becomes 1 underneath Cl, and Cl goes 1 as well. So they react together based on a 1-to-1 ratio. So the product is NaCl. So just keep in mind, just because there's a 2 here, I'm not going to force a 2 over here. It doesn't work like that. It just, whenever you write an ionic compound, it has to make sense based on the charges. And over here, since they both have a +1 and a -1, the ratio of the positive and negatives are equal. So we're good with writing it as as NaCl. And then once you write the product, now you can start balancing the equation. So we see there's a 2 on the Cl underneath the Cl. So anytime you have a subscript underneath an atom, that means it belongs to that atom. That means there's 2 chlorines on the left. However, there's nothing on the right. So because of that, I put a coefficient of 2 behind NaCl. So the way the coefficients work is that because it's both behind Na and Cl, it applies to both of them. So that means now I have 2 sodiums on the left and 2 sodiums on the right and 2 chlorines on the right as well. So because of that, now the number of sodiums are not balanced. So now I have to put a 2 over here to balance the sodium. Let's take a look at another example. So let's say now we have aluminum reacting with O2. Again, you have to think about what kind of compound are we making together. Is it an ionic or a covalent? Because aluminum is a metal and oxygen is a nonmetal, again, the charges matter. So aluminum has a charge of 3+, oxygen has a charge of 2-. So we switch the charges as a subscript underneath them. So the 2 goes here, 3 goes here. So the compound becomes Al2O3. Keep in mind, whenever you write an ionic compound, the metal has to go first and then followed by a nonmetal. You can never start with a nonmetal first. So now our compound is Al2O3. Now we balance it. So we see there's a 3 underneath oxygen. So there's 3 oxygens on the right, but there's only 2 oxygens on the left. So the only way I can make the number of oxygens match is by finding a common multiplier between them, which can only be 6. Because of that, I have to multiply this by a 3 to get 6 oxygens on the left, multiply this whole thing by a 2 to get 6 oxygens on the right. And this way the oxygens are balanced. And now we go to the next element, which is aluminum. So now we have 4 aluminums on the right. So we end up putting 4 aluminums on the left, and this is how we balance this equation. Okay, let's take a look at the second equation, second type of reaction, which is called decomposition. So the decomposition reaction is exactly opposite to synthesis. So what happens is a compound like AB either breaks down to its own elements or it breaks down to a compound and maybe its element. So it depends. So, we can take a look at some examples right now. So let's say we have something like KBr. So KBr, it's made from potassium and bromine. So there's no way you can make another compound out of this. So it can only break down to its own elements. So the elements are potassium, and bromine. However, certain elements, they're always in the form of a diatomic form, basically. So the diatomic elements are the ones that they're never sitting on their own. So when they're sitting on their own, they always are in the form of with a subscript of 2. There's always 2 of them combined together. So diatomic elements that you need to know and memorize and be familiar with are hydrogen. So hydrogen is always in the form of H2. Then we have nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. So these 7 are always in the form of diatomic. So when I write the product over here for Br, I can never put Br on its own. So Br, whenever it's formed, it's always in the diatomic form. So it's always Br2. So only these 7 elements are diatomic, nothing else. So now the products are potassium and Br2. And now because I wrote everything correct, now we can start with the balancing. So now we have 2 Brs on the right. So because of that, I put a a coefficient of 2 next to KBr. Now I have to balance potassium. Because of that 2 over here, potassium is now 2 on the left as well. So I put a 2 on the right. And this way we balance this equation. Let's do another one. Let's say we have something like NH3. So NH3 as well, it's just made from 2 different elements. So when it breaks down, it can only break down to its own element. So it goes nitrogen and hydrogen. However, if you look at the diatomic element list that I wrote on the right-hand side, both of them are basically there. So they both have to be in the diatomic form. So whenever you make nitrogen, it's in the form of N2. Whenever you make hydrogen, it's in the form of H2. And now these 2 elements are formed. And now we can start with the balancing. So for balancing, I have 3 hydrogens on the left. I have 2 hydrogens on the right. Again, the common multiplier between them is 6. So I multiply this by a 2, I multiply this by a 3, and now hydrogens are both 6 on both sides. And then we look at nitrogen. There's exactly 2 nitrogens on both sides. So this equation is balanced. Okay, so now we go to the next reaction type, which is called single replacement. So in a single replacement equation, some element it's sitting on its own, and then it's followed by a compound. And then what happens is the element can switch either with B or C depending on what it is. So let's just guess that here, for example, A and B switch. So A goes now sitting with C, and B is now going to be sitting on its own. But whenever you do write these reactions, you have to watch for what you're looking at. So for example, if A is a metal, it has 2 options. It can either switch with the metal of the next one, or it can switch with the hydrogen of the next one. Again, by putting these, I'm talking about switching. I'm not talking about putting them together. So A goes and replaces B, which is another metal, or if B is a hydrogen, A goes and replaces that hydrogen, basically. Or if you're dealing with a non-metal, so let's say if A is a non-metal, the one that it's sitting on its own, it can only switch with the non-metal of the second compound. So these 2 will switch. I'm going to show you some examples over here so that is more clear for you. Let's say we're talking about a case of magnesium plus Na3PO4. So here, magnesium is a metal. So what happens is that we said it can only switch with the metal of the next compound, or it can switch with the hydrogen of the next compound. So in the next compound, the Na is the metal and there's no hydrogen. So basically these 2 will switch. And that means magnesium now goes and replaces sodium. So magnesium now has to sit with PO4. And then Na is going to be on its own. However, again, because I'm making an ionic compound when Mg and PO4 are combined, I have to watch for their charges. So magnesium has a charge of 2+, PO4 or phosphate has a charge of 3-. So as we said, we can cross the charges. So the 2 of magnesium goes underneath PO4. So I need a bracket for that. And then the 3 of PO4 goes underneath magnesium. So this is how I make my compound for magnesium phosphate. And then sodium is not a diatomic, so it can sit on its own. And now that we guess the products right, now we can start balancing the equation. So for balancing, I see there's 2 phosphates on the right. So I put a 2 over here. As you can see, I'm balancing phosphates together. I don't break it down to phosphorus and oxygen separately. It's just easier because you see the phosphate is repeated on both sides. I can just treat it as one thing. So I say there's 2 phosphates on the right. So because of that, I need to have 2 phosphates on the left. So I put a coefficient of 2 over here. Now my magnesium, there was 3 of them on the right. So I put a 3 over here. And then last is sodium. There's 6 sodiums on the left. So I put 6 over here on the right. And this way we balance the equation. So this was the case of a metal switching with a metal in the compound. Now imagine the same thing, magnesium, but this time with HCl. So this is the metal now, and we're switching it this time with the hydrogen. So these two will switch. So what happens is that magnesium is going to replace hydrogen. So magnesium is going to sit with Cl, and hydrogen is going to be on its own. So a few things we have to watch over here. First is that magnesium and Cl together make us an ionic compound. So again, we have to watch for their charges. Magnesium is 2 plus, Cl is -1. So together they become MgCl2. And then hydrogen, if you remember from my previous slide, we said hydrogen is always a diatomic element. So it never sits on its own. So it has to be in the form of H2. Now we have guessed our products right. And now we can start with the balancing. So there's 2 Cls here. I put a 2 here. Hydrogen is balanced now. Magnesium is balanced now. So we're good with this one. Now let's take a look at this third example, which is a non-metal switching with a non-metal. So let's say we have MgF2 plus nitrogen N2, nitrogen gas. So what happens now is that nitrogen is the one sitting on its own. So it's a non-metal. So as we said, the non-metal can only switch with another non-metal. So it switches with fluorine over here right now. So these two will switch. So nitrogen is going to replace the fluorine. So magnesium and nitrogen are going to go together, and then fluorine is going to be on its own. Again, for writing magnesium and sodium and nitrogen together, we just said because this is an ionic compound, 2 things. First is that the charge matters a lot. So we have to put them based on their charges. And also, we always have to start with putting the metal first. In an ionic compound, always metal is written first, then the non-metal. So when we switch, we can see the compound becomes Mg3N2. And then looking at fluorine, fluorine is always a diatomic element as well. It was in that list on the previous page. So we always put it in the form of F2. And then we start with the balancing. So 2 nitrogens, good. I put a 3 here because of magnesium. And now it makes me 3F2 on the right-hand side as well. So this is how you write single replacement reactions. Now let's go to a double replacement reaction. So in a double replacement reaction, 2 compounds combine. Usually they're 2 ionic compounds. So AB plus CD, sorry, they don't combine, they react together. So what happens is that the metals of them will switch. So a metal will switch with the non-metal of the other one. So basically you end up getting A going with D and C going with B. So let's see some examples over here. Let's say we have CaSO4 plus KCl. So both of them are ionic compounds. So what happens is that the metal of the first compound, which is calcium, switches with the metal of the second compound, which is potassium. So technically calcium has to go with Cl, K has to go with SO4. But again, both products are ionic products. So we have to watch for their charges. So calcium has a charge of 2 plus, Cl is -1. So they become CaCl2. As we said, we have to switch these. And then same thing, K goes with SO4. So K is +1, SO4 is -2. So after you switch them, it becomes K2SO4. And now we guessed our products correct. Now we can start with the balancing. So 2 Cls on the right, I put a 2 here, 2 potassiums on the right, 2 potassiums on the left. Calcium is good. Sulfate is good. So as I said, sulfate, always take a look at it. Imagine it as one thing. So there's 1 SO4 on the left, 1 SO4 on the right. So we're good. So this is how you balance this equation. Let's try another one. Let's say we have magnesium chloride plus Na3PO4 sodium phosphate. Again, as we said, the metals have to switch. Magnesium is a metal, sodium is a metal, so you switch them. So now magnesium goes with the phosphate. I put some space because I haven't put the subscripts yet. And Na goes with the Cl. Again, the charges matter. Magnesium is 2 plus, phosphate is 3 minus. So together they make us Mg3 bracket PO42. And then Na is +1, Cl is -1. So together they're just a 1-to-1 ratio. So they're good right now. And then all we have to do now is to start with the balancing. So again, 2 phosphates on the right. So we need to have 2 phosphates on the left. So we put a 2 here, 3 magnesiums on the right. So we put a 3 here. Now 6 sodiums on the right, on the left, sorry. So we put a 6 over here. And then the chlorines, there's 6 on the left, 6 on the right. So everything looks good. So this is how you write a double replacement reaction. Next reaction type is called combustion. So in a combustion reaction, what happens is they usually give you an organic compound. So the compound can have carbon, hydrogen, and in some cases, oxygen as well. So I just don't know, like it can be various formulas. So I'm putting some random subscripts underneath them. So what happens in a combustion reaction is it's always combined with the O2 gas because O2 is the source of combustion. When you want to burn something, you always use oxygen gas. And the products are always CO2, which is carbon dioxide, and water. So these 3 are always there. So this is always there, this is always there, and this is always there. So your compound can be different every time. So here, writing the reaction is not very hard. It's just more about balancing. Sometimes the balancing can get tricky. So I'll give you a few examples. So let's say we have C3H8 and we're burning it, combusting it with O2. So as we said, to guess the products, we always make CO2 and H2O. Now for balancing, I always suggest balancing carbon first, then hydrogen, then oxygen. So over here, we have 3 carbons on the left. So we put a 3 here, 8 hydrogens on the left. So we put a 4 here. Now we look at the oxygens on both sides. So the number of oxygens over here is 3 times 2, which is 6, plus another 4, which is 10. So we have 10 oxygens over here. So we need to have 10 oxygens here too. The only way we can make 10 oxygens over here is by putting a 5 over here. So this equation is balanced. But now let's take a look at another case like C2H6 plus O2. Again, writing the products is easy, CO2, H2O. So we start with carbon first, 2 carbons on the left. So we put 2 CO2s, 6 hydrogens on the left. So we put a 3 here to match the hydrogens. Now we count the oxygens. So oxygens here, there's 4 here, 3 here. So we have 7 oxygens. So we need to have 7 oxygens here as well. So the only way I can make 7 oxygens here is by putting either 7 over 2 over here, because then when it's times 2, it's 7, or you can think about just not a whole number, like 3.5, for example. You can imagine 3.5 times 2 is 7. So you can write it for now like this, but we never want to leave a fraction or a decimal number as a coefficient. So what we do at the end is you can balance, basically multiply everything by a 2 to get rid of that. So basically our balanced equation would end up being 2C2H6 plus 7O2, giving us 4CO2 plus 6H2O. And now that is balanced. I'll show you one more. So this one, I'm showing you a compound that has oxygen in it too, something like it's an alcohol basically. So C2H5OH, let's say, plus O2. So again, the products are always CO2 and H2O. So first thing for this one, for balancing it, I suggest, because this compound has hydrogen, but it's written differently, like the 5 hydrogens are written first and then the hydrogen is written at the end. You can just, this is just a balancing thing. So you can just imagine this as being C2H6O. It's just the same thing. The way they're writing it is based on how the structure looks for an alcohol, because an alcohol like this looks exactly like this. So it's C2H5, like they're writing this part first and then they're following it by the OH. So it's just technically essentially C2H6O. So you can just write it this way. So you can think about it as C2H6O plus O2 give you CO2 and H2O. Now let's balance the carbon first. So 2 carbons on the left, so we put a 2 here. 6 hydrogens on the left, we put a 3 here. Now let's count the oxygen. So there is 4 and 3, so there's 7 oxygens here. Now, we need to have 7 oxygens on the right as well. However, this compound has 1 oxygen on it. So we only need 6 oxygens over here to balance that. And because of that, we can put a coefficient of 3. So our balance equation is C2H6O plus 3O2, giving us 2 CO2 and 3 H2O. Okay, so this was it for combustion. Now we go to acid-base neutralization. So in an acid-base neutralization, an acid is always combined with a base, and together we say it makes us a salt. By the way, salt is another name for an ionic compound and water. So these are the products of acid-base neutralization. So what is an acid? Acid is something that starts with an H normally. So let's say the general formula is HX. And then you have a base that usually follows with an OH. So let's say you have YOH. So what happens in an acid-base neutralization is the H of the acid combines with the OH of the base. So together they make us HOH, which is H2O technically. And you end up getting the salt as well. So the salt is the ionic compound, as we said. So first the metal goes first, followed by the non-metal. So that's how we put them together. So let's take a look at some examples. Let's say we have HNO3, and then we have KOH. So HNO3 is an acid. As we said, it starts with an H. KOH is a base because it's followed by that OH. So together, H and OH combine and they make us a water. And then K and NO3 together, they make us an ionic compound. So we look at their charges, +1, -1. So they go together as KNO3. And this is how we write the products, and now we can balance them. So in terms of balancing, I mean, sometimes it's easy to balance these, sometimes people have trouble with them. What I suggest to think about is that always the number of hydrogens of the acid should match with the number of OH of the base, and together they should make you the same number of waters. Let me write it as H2O. I find this the best way for balancing the acid-base neutralization reaction. So for example, here you say I have 1 hydrogen for the acid and the base has 1 OH. So together 1 H and 1 OH make you 1 water. And this way everything balances perfectly. I'll show you in another example. Let's say we have H2SO4. It's combined with NaOH right now. So here, as we said, the products would be water and then the salt or ionic compound, which is between Na and SO4. So Na has to go with SO4, but again, charges matter. Na is +1, SO4 is 2-. So together it becomes Na2SO4. Now, this is where I was saying I watch for how many hydrogens or how many OHs they all bring. So the acid is now bringing 2 hydrogens. So we said the number of hydrogens of the acid should always match with the number of OH of the base. So this is bringing 2 hydrogens, but the base is only bringing 1 OH. So because of that, I have to put a 2 here. So to make them match, so now we have 2 hydrogens for the acid, 2 OH for the base, and together they make 2 waters because we said their numbers are always the same. So we end up getting 2 waters, and this is already balanced. Honestly, if you try this any other way, you'll probably have more trouble. So I think this is a good way of thinking about balancing these equations. Let's take a look at another one. Let's say we have H3PO4, and we are adding it to SrOH2. So together, we have to write the water because it's acid-base neutralization, and the salt or ionic compound, which is between Sr and PO4. Again, we look at their charges because it's an ionic compound. So together it becomes Sr3, PO42 plus water. Now for balancing, we said the number of hydrogens of the acid and the number of OH of the base should match. So your acid is bringing 3 hydrogens, but your base is only bringing 2 OHs. So there's no way they're going to match by putting coefficients next to them. So the only way I can do that is by finding the common multiplier between them, which is 6. So because of that, I have to add a 2 over here. So this way my hydrogen is 6. And then I can put a 3 over here to make the OH to be also 6. And because of that, now we end up getting 6 waters and the equation is balanced. Yeah, so these were the six main types of reactions. Obviously, these are not the only ones. For example, we have redox reactions, or we have reactions of a carbonate salt or bicarbonate salt with acid. I'll show them in a different video because this video is getting very long. But the main six reactions that you're responsible to know and to do any stoichiometry question is basically these six. So I hope you enjoyed the video. If you did, please make sure you press the like button and subscribe for watching more tutorial videos. You can drop your questions or requests for new videos in the comment section. Hope to see you in the next video.